Hello, students. Now let's study Kepler's third law, the law of the periods. So Kepler's first and second law, which are presented in his book Astronomia Nova, deal with one-body motion, one planet that is orbiting a central object. The third one, which was published 10 years later in 1619 in his book Harmonices Mundi, is separate and deals with a system of planets. Now, having derived the distances and the orbital periods to the planets in the heliocentric model, Kepler noticed that they obey the regular relation. You may know already the relation, which is that the square of the period is proportional to the cube of the semi-major axis. So let's find out how Kepler got to this law. We can see Kepler's third law live if you observe Jupiter for a few nights. You're seeing here the four moons of Jupiter, four big moons of Jupiter on the approach of the New Horizons spacecraft. So this is a page from Galileo's Sidereus Nuncius. You can see here, spaced in some nights, observations of Jupiter and some of the moons. Sometimes you only observed a few of them, two of the moons, sometimes three of them. On a few occasions you observed the four moons, and here and here. And here the dates of the observations. So this is a representation of the same analysis that Galileo did to find the periods of the moons. So these are synthetic observations. So Jupiter is in the center, separated by 12 hours. So you can see here, you can trace the periods of the moons. The outermost is simple, right? That's Callisto. The other one would be Ganymede. So you got Ganymede here. You can trace it also with some reasonable accuracy. Getting the periods of Europa and Io is a little trickier because they are closer to Jupiter, but still, I once asked the class to do that, and these are the dots that they came up with. So you can average this, that's what you have. So these dots here has average. This is the distance to Jupiter in units where the distance between Io and Jupiter is equal to 1, and the time here in orbital period. Callisto is 16 days, Ganymede is about 8 days, Europa is about 3 days, and Io is like 1.5 days. So when you have this data, first thing that you want to do is to try to find a correlation. So let's try the easiest, which is to try to pass a straight line. There you go. A straight line does not fit the data. So let's try parabola. R squared also does not fit the data. So let's try something in the middle. So R doesn't work, R squared doesn't work. Let's try R to the power of 1.5. Bam, that's what you have. It works like a charm. So let's remove the other lines and the redundant data to show the relation. There is a clear relation between distance and orbital period for the moons of Jupiter. Now, this is not limited to the moons of Jupiter. It's also seen in the periods of the planets. If the planets are orbiting the sun, their orbital period is also correlated with the orbital distance, following the r to the power of 1.5. Now, because it is wonky to work with these fractional exponents, you can square both sides to find that the square of the period is proportional to the cube of the semi-major axis. So this summarizes Kepler's three laws of planetary motion: the law of the orbits, the law of the areas, and the law of the periods.